Welcome to another lesson of Math 1314, College Algebra. Today's lesson, our learning objectives will be to find the greatest common factor of a polynomial, to factor a trinomial, to factor by grouping, factor a perfect square trinomial, to factor a difference of squares, to factor the sum and differences of cubes, and to factor expressions using fractional or negative exponents. Let's get started. Let's first start with the definition of a greatest common factor. The greatest common factor of a polynomial is the largest polynomial that divides evenly into the polynomials. So, if we're given a polynomial expression, how do we factor out the greatest common factor? Well, first, we find the GCF of the coefficients. Then, we identify the GCF of the variables. We combine these to find the GCF of the expression. Then we determine what needs to be multiplied to obtain each term in the expression. So determine what the GCF needs to be multiplied to obtain the terms of the expression. And finally, we need to write the fully factored, not fully factored, but the factored expression as the product of the greatest common factor and the sum of the terms we need to multiply by, as referenced in step 4. Let's try an example. Okay, for this example, we want to factor out the greatest common factor of 3x cubed y minus 45x squared y squared plus 135xy cubed. The first thing we need to do is identify the GCF of the coefficients 30, 45, and 135. The GCF of those numbers is 15. That's the greatest common factor among those. Then we need to look at the variables to find the GCF of the variables. So we have x cubed y, x squared y squared, and xy cubed. So the thing that we have in common among those is x. We have an x in each case, and we have a y in each case. Our next step is to determine what the GCF needs to be multiplied to obtain each of the terms in the original expression. So 15xy times what gives us 30x cubed y? Well, 15 times 2 is 30. X times x squared is x cubed, and y times 1 is y. So in the next one, we need to get 15xy times what gives us negative 45x squared y squared. Well, 15 times negative 3 gives us negative 45. X times x gives us x squared. And y times y gives us y squared. Finally, 15 times what gives us 135? Well, that's 9. And x times 1 gives us x, and y times y squared gives us y cubed. So if we were to distribute this back out, we would get 15 times 2 is 30, x times x squared is x cubed, y is just there, y times 1. We have 15 times negative 3 gives us negative 45, x times x is x squared, y times y is y squared, and then 15 times 9 is 135, x times 1 is x, and then y times y squared is y cubed. So this is the fully factored version, and our GCF is 15xy. Let's now talk about factoring a trinomial with a leading coefficient of 1. A trinomial, 3 terms, of the form x squared plus bx plus c can be written in factored form as x plus p, x plus q, where p times q is equal to c, and p plus q is equal to b. So one of the first questions we need to ask is, can every trinomial be factored as a product of binomials? Well, no. The answer is that some polynomials actually can't be factored, and we call those prime polynomials. So if we're given a trinomial of the form x squared plus bx plus c, we want to factor that. Well, we first find the factors of c. The next thing we need to do is find p and q, which are factors of c whose sum, p plus q, is equal to b. And then finally, we can write the factored expression as x plus p, x plus q. Let's try an example. Let's factor x squared minus 20x plus 100. So our first step is to list the factors of 100. Well, we have 1 and 100, we have 2 and 50, 4 and 25, 5 and 20, and 10 and 10. So if we add these two factors, or a pair of these factors, which pair of factors sums to 20? Well, 1 and 100 would not give us that. 2 and 50 wouldn't. 4 and 25 would not. 5 and 20 would not. 10 and 10, though, if you do 10 plus 10, you get 20. So if both of those are negative, then we get the negative 20 that we need for b, which is negative 20. So we can then write this as x minus 10 times x minus 10. That's how we factor it out. Now, if we wanted to verify and redistribute, we can double distribute. X times x gives us x squared. X times negative 10 gives us negative 10x. And we move to the second term. Negative 10 times x gives us minus 10x. And negative 10 times a negative 10 gives us plus 100, which gives us x squared minus 20x plus 100, as we started with. Now we'll see here in a few moments how this is sort of a special case, but I wanted to start with that example. Let's do another. Let's do another example. Let's factor x squared plus 2x minus 15. So we have this trinomial whose leading coefficient is 1, where b is equal to 2, and c is equal to negative 15. We need to find the two numbers with a product of negative 15 and a sum of 2. So, what are the factors of negative 15? Well, you have 1 and negative 15. You have negative 1 and 15. 3 and negative 5. Or negative 3 and 5. Well, what do those sum to? Well, those sum to negative 14, 14, negative 2, excuse me just a second, let's rewrite those so it makes more sense. Negative 14, 14, negative 2, and 2. So which set of factors do we want to use? Well, we want to use the negative 3 and the 5 because that gives us a sum of 2. So we can factor this as x minus 3, x plus 5. And then we could go back and redistribute to verify that this is correct. Now that's something that you should do on your own for homework, is verify that this is the case. So now that we've dealt with factoring trinomials with a leading coefficient of 1, we need to move on to discuss factoring trinomials with a leading coefficient that is not 1. So we need to discuss factoring by grouping. To factor a trinomial of the form ax squared plus bx plus c by grouping, we need to find the two numbers whose product is a times c and whose sum is b. We can then use those terms to divide the x term into the sum of two terms and then factor each portion separately, and finally factoring out the GCF of the expression. So what are the steps? To factor a trinomial of the form ax squared plus bx plus c by grouping, we need to first list the factors of AC. Then we need to find P and Q such that P times Q is equal to AC and P plus Q is equal to B. We will then rewrite the expression as ax squared plus px plus qx plus c. Then we factor out the GCF of ax squared plus px. We factor out the GCF of qx plus c, and then finally factor out the GCF of the entire expression. Well, what does this look like? Let's do an example. Let's factor 2x squared plus 9x plus 9. We first need to start with the factors of a times c, which is 2 times 9, or 18. Well, we have 1 and 18, 2 and 9, and 3 and 6. So what factors, when we take the sum, do we get 9? Well, the sums are 1 plus 18, which is 19, 2 plus 9, which is 11, and 3 plus 6, which is 9. So by grouping, we can say that 2x squared plus 9x plus 9 is equal to 2x squared plus 6x plus 3x plus 9. So now we'll consider the various parts of this. We'll start with just the first two terms, and then we'll consider the last two terms. So what is the greatest common factor between 2x squared and 6x? Well, we know that we can factor a 2 out. We can factor an x out. So 2x times what is 2x squared? Well, that is x. And then 2x times what gives us 6x? Well, that's a positive 3. So we know that we can factor out an x plus 3 here. And then in the second set of terms, we can factor out a 3. And 3 times what gives us 3x? Well, that's just x. 3 times what gives us 9 plus 3. So what we've done now is we've been able to factor out an x plus 3 from two sets of terms, which means that's the greatest common factor of the entire expression. So we factor out an x plus 3, and we're left with 2x plus 3. The 2x comes from the first set of terms and the 3 from the second. So our fully factored form says that 2x squared plus 9x plus 9 can be factored as x plus 3, 2x plus 3. Let's do another example. Let's factor 6x squared plus x minus 1. Well, in this case, a times c is equal to negative 6. What are the factors of negative 6? Well, we have 1 and negative 6, negative 1 and 6. We have negative 2 and 3, negative 3 and 2. Are there any other factors? I can't see any. What are the sums? Well, 1 plus a negative 6 gives us, it gives us a negative 5. Negative 1 plus 6 gives us a positive 5. Negative 2 plus 3 is 1, and negative 3 plus 2 is negative 1. So which one do we need? We need the factors negative 2 and 3 because we need the sum to be 1. So we can rewrite this expression as 6x squared minus 3x plus, not minus 3x, minus 2x plus 3x minus 1. So we consider first just the first two terms. What's the greatest common factor of those two terms? Well, we can factor out a 2x, and we're left with 2x times what gives us 6x squared? Well, that's 3x. And 2x times what gives negative 2x? Minus 1. And then in the second set, we need to factor out what? Well, we just have 3x minus 1. So it looks like that's a 1 times 3x minus 1. So we can factor out the greatest common factor of 3x minus 1, and we're left with the greatest common factor of the first set, 2x, and a plus 1. Now again, you can verify this by double distributing to get back to our original expression, 6x minus 1. Let's talk about a special case of factoring with trinomials called factoring perfect square trinomials. A perfect square trinomial is one that can be written as the square of a binomial. And it looks like a squared plus 2ab plus b squared, which can be written as a plus b quantity squared. Now, sometimes it may be hard to recognize a perfect square trinomial, but if you can look at something and figure out that, oh, well, I have the term on x squared, or the term that is squared, is a square something, and then the final term is something squared, and then the middle linear term is 2 times the coefficient of a and the coefficient of b, then I can rewrite it in this way. The first thing that we need to do to check to see if one is a perfect square is to confirm the first and last term are perfect squares. The second step is to confirm the middle term is 2 times the product of a and b. And then we can rewrite as a binomial a plus b squared. Let's do an example. Let's factor 49x squared minus 14x plus 1. Well, given that we're talking about perfect square trinomials, you expect this to be a perfect square trinomial. Well, the first thing that we need to check is to verify that the first and last terms are perfect squares. Well, 49 is a perfect square, and x squared is a perfect square. So we check that box on the first one. Is 1 a perfect square? Well, what's the square root of 1? It's just 1. So 1 squared is 1, and so we have a perfect square. So what is a in this case? Well, a is equal to 7 x, right? Because 7 squared is 49 and x squared is x squared. And b, what is b? B is equal to 1 is 2. What is 2 times a times b? Well, 2 times 7x times 1 is equal to 14x. So what does that tell us? Well, that says that we can rewrite this as a plus b quantity squared. So we have 7x. Is it plus 1 or minus 1? Well, in this case, it's minus 1 because we want that to end up being negative 14. And so if we want to test this out to verify, I will, in this case, expand it out. To rewrite this 7, it looks like a 2. 7x times 7x is 49x squared. 7x times negative 1 is minus 7x. Negative 1 times 7x is minus 7x. Negative 1 times negative 1 is plus 1, so we're left with 49x squared minus 14x plus 1. So recognizing the perfect squares in the first and last terms and the product being twice a and b helps you to be able to factor this special case. Now, could you have factored it some other way? You absolutely could have factored it by grouping like we've discussed before, but this is just a special case that factors much more easily. There are another few special cases that we'll now consider. Another special case that we consider is factoring the differences of squares. So let's do a definition. A difference of squares can be rewritten as two factors containing the same terms but opposite signs. In other words, a squared minus b squared, a difference, meaning subtraction, of squares, things that are squared, is the same as a plus b times a minus b. So how do we determine if we have a difference of squares? Well, we confirm the first and last term are perfect squares. And we rewrite in factored form as a plus b, a minus b. Let's consider an example. What if we had 81x squared minus 100? Do we have a difference of squares? Well, we have 9x quantity squared minus 10 squared. So our a is 9x and our b is 10. So we can rewrite this as 9x plus 10 times 9x minus 10. We can verify this is correct by redistributing. 9x times 9x gives us 81x squared. 9x times negative 10 gives us negative 90x. 10 times 9x gives us a positive 90x. And 10 times negative 10 gives us minus 100. These two middle terms cancel out, and we're left with 81x squared minus 100, which is exactly the same as what we started with. So our fully factored form is 9x plus 10, 9x minus 10. Now we need to discuss factoring a difference and sum of cubes. So we can factor the sum of two cubes, a cubed plus b cubed. We can factor that as a plus b, a squared minus ab plus b squared. And similarly, we can factor a difference of cubes as a minus b, a squared plus ab plus b squared. Let's consider an example. Let's consider 216a cubed plus b cubed. Well, we can rewrite this in a way that has the two cubes separated. So what is the cube root of 216? It's the undoing function. Well, it is 6, and we'll have the a, so 6a cubed plus b cubed. Well, how can we rewrite that? We can rewrite that as 6a plus b times the quantity 6a squared minus 6a times b plus b squared. So one more rewrite, it's 6a plus b. Well, 6a squared is 36a squared minus 6ab plus b squared. And that's our final answer. Let's do another example. Let's factor out x cubed plus 512. Well, we're assuming that 512 is a perfect cube, and it is. We can rewrite that as x cubed plus 8 cubed. And using the formula for a sum of cubes, we get x plus 8, x squared minus 8x plus b, which is 8 squared, so 64. And that's our final answer. Let's factor this difference of cubes. We have 1000x cubed minus 1. Can we rewrite this as a difference of cubes? Well, yes, we can. The first thing we need to do is recognize that 1000x cubed is the same thing as 10x cubed minus, and 1 is a perfect cube, minus 1 cubed. Okay, from the formula that we get for a difference of cubes, that means we can rewrite this difference of cubes as 10x minus 1 times the quantity 10x squared minus 10x times 1 plus 1 squared. Okay, that remains the same in the front, so 10x minus 1. Now notice that we have in brackets there 10x squared. That actually gives us 100x squared because you have to distribute the exponent down into the 10x. You have two factors of 10x, so that's 100x squared minus 10x plus 1. Let's consider one last example where we're factoring an expression with a fractional or negative exponent. So in this case, the same rules apply for factoring with integer exponents. So the first thing we will want to do is to factor out the term with the lowest value of the exponent. The lowest value of the exponent is a negative 1/4 on 5a minus 1. So 5a minus 1 to the negative 1/4. And then we need to figure out what we can multiply that by to get our original expression. Well, 5a minus 1 to the negative 1/4 needs to be multiplied by 2 times to get the 2. And then 5a minus 1 raised to the 1 power gets us the negative 3/4 plus a 7a. Okay, so we can distribute on the inside. We'll copy the first term, 5a minus 1 to the negative 1/4. And we'll have 10a minus 2 when we distribute the 2, plus a 7a. And then we can combine like terms inside the brackets. 10a plus 7a is 17a minus 2. And that's our fully factored form of this problem. That concludes section 1.5, Factoring Polynomials. If you have any questions, be sure to email me.